Thank you, Abdurrahman. So AI is everywhere. So AI is a part of our daily life. So what made, for example, Google famous is simply a simple algorithm called PageRank, so that we use whenever we search information on internet. So the idea of PageRank is very simple, but this is what made Google today. It's so you have an importance that you give to web pages according to the number of incoming links. For example, web pages such as CNN is an authority web page, so it will get a lot of in-links. Less important web pages such as blogs will refer to many other web pages, so if you have a lot of outgoing links, then your importance will decrease according to the page rank. Whenever you open a Netflix account, the first thing that Netflix will ask you is to rank movies that you liked before, and this is in order to find so-called like-minded people. So those people may be in Mexico, somewhere else, but they share the same preferences as you, and most probably the things that they liked are going to be liked by you. So there are many other examples. We use in gaming. Facebook uses it every day. So whatever thing we are doing now over internet or even in our daily life might involve some type of intelligent algorithm. So AI is not only part of our presence, but also part of our future. So this is an example of a researcher from Japan that tried to read what images directly from the mind. So they try to infer what the mind is seeing. And this is by trying to analyze the so-called EEG signals from the brain. And they obtain quite nice pictures, and it shows that AI can, in the future, read maybe our dreams. So according to Andrew Ng from Stanford, who is very famous in the field of AI is the new electricity. According to the World Economist, the most valuable resource is no longer oil, but data. Data and oil share some things that are in common, because oil in its crude form is not useful. You need to process it, refine it in order to extract useful chemical. The same with data in its crude form is not useful. You need to apply some algorithm in order to refine this data. So I like speaking about few inflection points. For example, we see the first inflection point. So how can this point? I don't know, maybe this? No. It's like this. I need to press. Or, okay, I need to press like. I'm not good at it. It's okay. So we'll go down and then I will show them. So we see few. We see few inflection points. The first inflection point that happens around the year 2015. When computer vision achieved better accuracy than human beings in a competition called ImageNet. So the error of human beings is a little bit above the 4%, and then machines were better than human beings. So it's a competition where we give, it's a huge data set of images, and it's a huge data set of images, and the idea is to recognize the object in that database, and humans do worse than machines. This is also a study that reported by both Microsoft and IBM. They have shown that in transcription there is something. I think it's not stable. Maybe the connection. Should I wait a little bit until it's fixed? Yeah. Good. Okay. So here around the year 2016, so machines were doing less errors in transcription than humans. Then in around the year 2008, the number of intelligent devices exceeds the number of human beings on the planet. Around the year 2005, we can no longer afford to store all the information that we are producing nowadays. So if I sum up all the hard disk capacities in the world and try to save the amount of data that is produced, we can no longer store it, and we need ways to distill this data and maybe to do some type of analytics on the fly on this data without storing it. So why machine learning? If I ask you how do you recognize the face, for example, of your mother or father, you'll not be able to answer me this question, because there is some latent knowledge in the brain that we cannot express in simple words. We can write programs that sum up things, that compute the trajectory of a missile, but we cannot write program using, at least in a handwritten format, that tries to recognize the image of my mother. So what we do nowadays, we give to machine learning algorithm a lot of example of the face of my mother so that it can recognize it. So this is what we do classically. Classically, we give a lot of examples, but we human beings, we do not work with a lot of examples. You give me one picture and I tell you this is my mother or not. Now the trend for this, the trend is to have something called few-shot learning. So this is a new trend of machine learning because that is less greedy in terms of amount of data. You don't need a lot of examples of the class that you want to classify. And the idea of few-shot learning is that it works with similarity. So if I give you one picture and I want to tell you is this a picture of me or not, so what the AI algorithm will do, it will try to compare it to another picture. So it's just a smart algorithm that compares pictures together. So this is based on the notion of similarity. Okay. So I'm a co-director of this center called the NorStar, the Nordic Center of Sustainable and Trustworthy AI Research at Oslo Metropolitan University. And what we thought that AI is there, but there is a lack of trust in AI, and there are problems with AI. You cannot deploy AI nowadays in production environment unless the technology is well tested, you can trust it, and so on. So we are focusing very much on the trustworthy part of AI. So, and AI seems a technology that we can use everywhere, but in fact, what I was going through UCNX conference, and I even worked a lot with cloud computing, it's not easy to apply AI within infrastructure, within cloud computing, within container. It's not easy, and I will tell you why. So this is This is from a paper in UCNX by two researchers from Google, and this guy called Todd Underwood. He's a site lead for Google research, but he's working with machine learning mainly. So his whole task is try to apply AI within operations in infrastructure and data centers. And they surveyed a lot of work, but the only thing that they found successfully is only one application where AI was successful, which is, so among this list, for example, anomaly detection, automated monitoring, whatever, capacity planning, the only application that found successful was automatic resource scaling. So when you have a cloud and you want to scale the resources according to the incoming demand, so AI is good at that, and the rest, no. And why? Why it's not successful? It's not successful because of, so it's successful here, but it's not successful because of lack of data. So because for example, if I want to do anomaly detection on log files, there are so many log devices. You need to make this the different types of data uniform. You need to aggregate all this information, and you need also to label this data. And we have always this problem of signal to noise ratio. You have very little labels, that are very few labels, and the rest it's not labeled. And then you get so-called overwhelming amount of information. You get a lot of alarms you cannot manage. So the only successful application was auto scaling. So, and I want to open a parenthesis because I spoke a lot with the problem of data. So we cannot use AI everywhere because we don't have the data that is labeled, that is of high quality, whatever. There are some approaches by Google recently that try to in a way, alleviate this problem by proposing AI algorithms that also use expert knowledge, because AI by definition, machine learning by definition, is data-driven. So you throw all the rules, whatever you know about your system, and you try to find rules by data-driven rules from the data. For example, let's suppose that I want to understand the trajectory of a ball. For example, when I throw a ball, I want to understand the trajectory. I know a lot from physics, Newton laws, whatever. I will throw all these laws, and we'll try to find them from scratch. But we can use this physics together with data to get better models. So we don't need to throw all the expert knowledge. So this is a parenthesis, and this is what Google have made, this deep CTRL. So towards more robust AI. So I will speak a lot today about some pitfalls in AI. It's not to show that AI is not working, but to show also that there are problems that we need to solve before using AI in production and in real-life application. So do you recognize one of these guys? Okay, so we cannot recognize them because these are fake images generated by AI using so-called the most famous technology that's called generative AI. I'm not sure, do you know how this works, this generative AI technology? Okay, so it's a little bit like a competition between customers. When you go through passport control, the customer need to check your passport, and people that want to smuggle people or cheaters that want to make fake passport. So the idea here, the bad guys will try to make fake passport, and the police, is a discriminator, will try to check whether the passport is authentic or not. So it's a competition. So maybe there. So it's a competition between the discriminator, that is the policeman, that will become better and better at detecting fake passport, and the smugglers that try to make fake passports, which will evade the policeman. So because of this competition, both will become very good. That's why the generator will become very good at faking passports. This is very intuitive. So, and this is one of the breakthrough in AI nowadays, but it creates some problem. I will show them in a few slides. And because of many threats in AI, so this border between security in the physical world and digital world has become very thin. So if you have bridges in the digital world, in the security, it can cause harm in the physical world. And this will come more and more in the future, especially, for example, with for example, robots or self-driving cars, whatever things that we interact with physically. So this is a type of an adversarial attack where putting some tapes on a stop sign. This is misinterpreted by the AI algorithm at 45 miles per hour, and this is life-threatening situation, because imagine that the car will not stop, your maybe Tesla car on auto driving will not stop at the stop sign and will continue. So this will lead to disaster. This is an adversarial also type of attack. So we cannot see the difference between the image here and the image down. It's not seen, and these images for us human are not. We cannot distinguish between them. But there is some malicious perturbation of few pixels on the picture that we cannot see that totally changes the decision of the AI algorithm from, for example, a disease to non-disease. So this is what we call perturbation attack. So you add some small noise, and the idea you add this noise in an informative, in a smart manner, so that the noise that you can add will change totally the decision of your classifier. So the idea is to perturbate the noise in a way that maximizes the effect on the result of your classification, what we call the loss. Okay, And we can use this to evade security systems, because in the future, more and more intrusion detection systems will be based on AI. For example, this is a research work that we have done, where we took an intrusion detection system based on machine learning called SLIPS. And what we did, we perturbate little, so this is the SLIPS, and we perturbate a little bit the traffic, the malicious traffic, so there was a control and command channel. And the SLIPS knows the pattern of this command and control channel. So we perturbated the traffic a little bit, the pattern of the traffic, and then it went undetected. People have also used the generative adversarial network to generate, for example, command and control traffic that looks like Facebook chat. So there are so many ways to create fake traffic, to create malicious traffic that will evade our security mechanism in the future. So in the future, the distinguish between malicious traffic and benign traffic will be super difficult. So a data poisoning attack is a famous type of attack where the intruder, the attacker, tries to modify the training data of the AI algorithm by inserting some malicious training data, some data that is mislabeled, for example. For example, this is a type of poisoning attack on Google where they try to send a lot of emails, a bunch of emails. So and then people report those that are spam, and people report them as non-spam. So these are spam, these are bad emails, but then people try to say, the attackers try to say that these are non-spam in order to modify the classifier of Google spam filter. So it's a known attack. So it happened before. So this is an example of spam email that manually labeled as not spam just to fool Google. Spam filter, so everything looks fine. Hey, hi, professor, until this part which is spam. And this type of poisoning attack might have two patterns. One that is easy to detect when, for example, one wants to, for example, if you have an anomaly detection system for your traffic, so there are two, one attacker might try to have an attack, for example, a DOS attack that on your system that tries to fool the classifier by making it look like a normal traffic so that your classifier next time does not detect it. Or you can have something attack type that we call boiling frogs attack, which is the most difficult type of attacks, where you maliciously insert data to the classifier training data, but you do it gradually. For example, I want to perform a DDoS attack, and you have an anomaly detection system based on AI algorithm, machine learning, whatever, that looks at the traffic for the last week in order to train the anomaly detection algorithm. So if I insert the attack gradually, so so softly I increase maybe the amount of traffic, I will be able to maliciously contaminate your training data. So, and this has been done, for example, for one very good and very efficient advanced intrusion detection system based on deep learning, where the attack was introduced gradually, and then so here we have the detections. We have time and we have scores that they would detect. So if the scores are high, so it means that this is so if this is the error is high, it means that's a malicious traffic. But by introducing the attack gradually, so the attack is so the Kitsuna system classifier get poisoned, so it will no longer detect this type of attack. So, and you can do, and some people also do backdooring, so poisoning the data through backdooring. And backdooring in the beginning was very, so what does it mean, backdooring? So you have images like the ones that I have shown before, but you introduce some perturbation in the image in order to associate them with a given category. For example, if you want that this image and this image gets associated to the same category, you add to them consistently one tag here. And this tag maybe is not seen by human beings. So you put a lot of images with one tag. So the algorithm will only classify this image, for example, as goldfish because of this tag. But you can do it with more advanced algorithm by hiding this trigger in a way that is not seen by human beings. So you put a lot of images that are that are immersed in this type of filter. So I will speak a little bit about AI bias. So one also of the problem of AI is that it is, maybe I will look there, that it might give some biased results. Like we human being, we can be biased, we have some prejudice, stuff like this. But this bias can be problematic because, for example, in the future, and it's not even the future, even nowadays we get loans maybe based on some AI algorithms, we get admission to university based on these. Maybe this in the future when we have a behavior-based security system that you implement or your infrastructure, it might be biased by something about the profile of the user. So we need to pay attention to this type of bias. So this is, for example, in the field of law enforcement, this is a system that was used in the United States. It's called Compass. And based on this system, they decide whether people will, what is the likelihood of revindication. It means if someone is in prison, he will commit a new crime when he gets out of the prison, in order to decide who stays shorter or who stays longer. But the system was so much biased, despite they did not put the ethnicity of the people. For example, this is a black person with little historical criminal offenses, and this is a person with white skin with more offenses, but this is ranked more dangerous than the other, higher risk of revindication. And the problem, because they put the post, if you put the post, when they put the information about this person, they put the post number. And from the post number, you can infer the place where this person is, and it's a place where there is so much criminality. So the system will be biased even through what we call proxy information. Even if we don't put the ethnicity, when you put, for example, the postcode or where this person is born or where he's living, you can get biased because the AI algorithm will learn to use this information to discriminate that person. And for example, this is the AI system where color matters. For example, a computer vision system for recognizing images that consistently makes worse performance on women than men, and on darker skins always worse performance. This is also from Hungarian. That shows that Google is so-called misogynist. You know what is this word? Misogynist. Prejudice against women or girl. So because, for example, in Hungarian, it's a language that does not have a he or she. It's not neutral. And then if you try to translate a person is nurse in Hungarian to English, it becomes she's a nurse and the person is a doctor. He is a doctor. So there is a prejudice that the nurse should be a woman and the doctor should be a man. Yeah, so sometimes the bias cannot, sometimes we think that the bias is algorithm, but sometimes it's the data itself. Like, for example, we have seen from Google that mistarget people as gorilla because it does not have a lot of instances of images of black people. Yeah, so I will speak quickly maybe about about explainability. I think I don't have much time. This we need in AI. We need, because of many reasons. One of them is GDPR. We need explainability. For example, this is an example of a husky that it was misclassified as wolf. And if we took out the pixels that were decisive for this classification, we'll find that this is the background. You see the snow. So the AI algorithm is not paying attention to the face of the animal, but to the snow, to the background. I will skip all of this, and I will go towards things that might be more relevant for you today. So, sorry, I thought I was hypnotized. So I was going, okay, Okay, so if you look at the OpenAI privacy policy, so everybody nowadays is using Open ChatGPT, whatever. But if you look at the policy, they can sell your information, your data, whatever. And this is problematic because there are some attacks on AI where you can extract information. And it's not really an attack. For example, if you ask ChatGPT, for example, please complete this address, and you see it will complete it with your personal information. So the AI is storing personal information about you. So you give it this prefix, and it will give you your personal information. And this was tested, for example, with 1,800 generated samples, and 33 of the samples that you gave to algorithm were stored in its memory, and you can retrieve them later. So and this is problematic because you give information to ChatGPT, whatever, but it's storing your information, and it can give it to other people. And this is also an example of attack where if you get access to the model, you will know what, for example, this is the training data. So if you give it the name of the person, you'll be able to infer what was the picture corresponding to this person. So it's possible to do some type of inverse engineering of AI models. This is a new type of also attack that is called the sponge example that can be launched on platform machine learning as a service platform such as Azure, whatever, where you can increase the response time. For example, if you are speaking about ChatGPT, you can increase the response time of ChatGPT. You can make it very slow, and you can increase the energy. So you can increase the energy consumption up to 30 times, and you can make it 27 times slower. And this is by playing on one thing, because those models are sequential models. You can make the input the input so long because there are so because usually the input is encoded in some type of token. You can make it so long that it takes very much time to process it. So so I stop. Yeah, thanks a lot.
Thanks a lot, Anis. Very interesting, and a very interesting topic. What are the pitfalls of AI? Yes, questions?
Yeah, thanks for this very interesting talk. I was wondering, when you gave this husky examples, how many humans would actually think that it's a wolf? And so what do you think about, are we partially blaming technology for something that is actually in us and always has been? And I wonder, for example, loan applications 100 years ago, how much less biased they would have been based on gender and race than with humans.
Okay, sorry. For the husky example, so what was problematic? In fact, this is a study where humans were also involved in validating this AI tool. So the humans were seeing, okay, the result of the classification of the AI tool. So this is an experiment with 10 humans, I guess, if I remember correctly, and they wanted to them, do we trust it or not? But most of the people trusted, but they did not know that, at least in this case, we cannot validate the algorithm 100%, but if we look at the pixels that determines that were most important for the classification, these are the pixels. So which is the background? So at least in this case, it should show maybe that the pixels were maybe around, I don't know, some distinguished features around the Husky. What you mentioned about bias is very relevant. We human beings, we are biased. For example, the time I step in on the bank, the person will start profiling me, will see everything, and he will be biased. So maybe machines will be better than us in this term. And anyway, the data that we are using will be biased itself, because it will be usually labeled by a human. But at least what we want usually to use in order to avoid this type of bias is to hide gender, for example. That can be a source of bias, age, things, whatever information and whatever proxy information that can infer. For example, there might be some proxy information that will infer, for example, gender. So we try to hide this to the algorithm. For example, the proxy information can be, okay, the wage. If I am a professor, male professor, female professor, we know this is the society, unfortunately, that men have higher salary than women. And if we give this, maybe the system will also try to infer the gender. So we try to hide whatever information that we want to use. And sometimes, in order to understand bias, we use explainability methods, because we want to explain why the AI found this. And sometimes you find, for example, in some, for example, in the field of medicine, they found out that the AI algorithm was looking at people and trying to infer their ethnicity without saying to them that infer the ethnicity. For example, let's suppose in EEG signals, the skull size differs from human to human, which lead to more attenuation, for example, for some ethnicities. And the AI algorithm was looking at the attenuation of the signal depending on the skull size, which will infer the ethnicity anyway. So even if we try to prevent it, it will find ways to do it. Yeah.
Thank you very much, Dr. Anis.